So our next type of potential energy is chemical potential energy. This is one you're probably familiar with because it involves you every day of your life. Potential energy is stored in the chemical bonds that hold the chemical compounds together. So when you eat, you are releasing the potential energy in the food that you are eating. There's chemical potential energy in the food that we eat. We also have batteries. Gasoline is another example. Coal that we burn to produce energy or electricity, that would be another example of chemical potential energy. Even matches have chemical potential energy in the tip that allows them to burn. So if atoms have very strong bonds, they're not very likely to break. The potential there to break them is very low. So we say that they have low potential chemical energy. You can't break them. It takes a lot of outside energy to break those bonds. So very low potential to be broken, low potential chemical energy. Weaker bonds have a lot more potential chemical energy because they need just a little bit of energy to break. The potential to break them is much greater. So weak bonds have high chemical potential energy. With electrical potential energy, you need to think back to what happens when we have positive charges and negative charges. Positive, repel. Negative, repel. It's when they're opposites that they are attracted to each other. So electrical potential energy is the energy associated with the position of the electrically charged objects relative to each other and how much charge they have. So how much charge they have and how close are they together. And that determines the electrical potential energy. The rule of thumb with this kind of is if you're making the charge do something it does not want to do, it has high potential energy. If it's doing what it wants to do, it's low potential energy. So in this graphic, we have a positive charge. It does not want to be by the positive charges. Like charges do not want to be together. They repel. So the closer you bring this positive charge to those other positive charges, the more potential energy you have. As you get that positive charge further away from the positive charges, the other positive charges, you're going to have low potential energy because it wants to go to that negative charge. So the closer it gets to where it wants to be, the lower your potential energy. So again, potential energy increases if the particle is moving the direction opposite of the field force. If you are forcing it to do what it doesn't want to do, positive together, negative together, you have a high electrical potential energy. If you get that positive charge by a negative charge, you have low potential energy. As it gets closer and closer, the positive negatives together, you have less and less potential energy because you're moving in the direction of the field force. They want to be together when they are opposite charges. So here we have a test charge, A, and we have a big plus sign. If we get this plus A charge closer to our big positive charge, it will have more potential energy because we're forcing it to do what it does not want to do. If it starts at B and we move it to A, it's going to have less electrical potential energy because we are moving the positive charge here at B further away from the big positive charge, which is what it wants to do. It wants to get away from it. Remember, those like charges repel. So if it's doing what it wants to do, low potential energy. If you're forcing it to do what it does not want to do, it's going opposite of that field force. You have high potential energy. So here we have a monkey. And he is going to force that positive charge to come closer. And as he's doing that, he's getting more and more potential energy. And if he lets go accidentally, you can see that that positive charge will move away. So as he brings it closer to, you have more and more electrical potential energy. And then once he lets go of it, it gets less and less as it moves away because it's moving the direction it wants to go. When he brings it towards the big positive, you're forcing it to do something it does not want to do. So more and more potential energy as it comes towards. As it moves away, because that's the way it wants to go, that is less and less potential energy. Magnetic energy kind of works the same way. Now, magnetic potential energy is the energy that's associated with the position of magnetic objects relative to the magnetic field. So, if they are attracted to the magnet and move closer, you have less potential energy because they want to be together. If you've got a North Pole and a South Pole and they want to be together and they move closer and closer, they have less potential energy because they want to be together. They're moving in the right direction here. They want to be together, so they're going to try to come together. Less potential energy. When you try and move them away from each other, you're going to be increasing that potential energy because they don't want to be away from each other. They want to be close to each other. If you were to flip the magnet of one of them around and now you've got south and south together, you have more potential energy because you're forcing them to be together. The closer you bring them, you're trying to force them together. So that would give you high potential energy because you're forcing them to do something they don't want to do. If you were to move it away, south-south away from each other or north-north away from each other, you would have less and less potential energy because that's the way they want to move. All right, please make sure that you can explain this meme to Mrs. Domingo. My physics teacher said I had potential, then he pushed me off a building.